Okay, we're going to look at a problem in which you have to find the electric field produced by two charges. And this is going to be just the one-dimensional case, so the two charges and the point where we're looking at the electric field all lie within a line. I already have my diagram set up, but here's the problem. A charge of minus 15 nanocoulombs is located at the origin, and a charge of minus 20 nanocoulombs is located at x equals 0.035 meters. Find the electric field at a point P located at x equals 0.010 meters. So I have Q1 labeled at my origin. I have Q2 labeled at 0.035 meters. And I'm also going to label my point P, which is at 0.010 meters. Label that a point capital P. So let's just start by listing our givens and unknowns. Our givens include Q1 is equal to minus 15 nanocoulombs, and the location of Q1 is x equals 0. Q2 is equal to minus 20 nanocoulombs, and the location is x equals 0.035 meters. And our unknown is then just going to be the electric field at x equals 0.010 meters. That's the electric field at our point P. Before we actually get started with the calculation, we should kind of figure out what we're going to be doing. We know that the electric field at point P is a combination of the electric field from Q1 and Q2. So we're going to need to find the electric field from Q1, find the electric field from Q2, and then add those electric field vectors. Electric field is a vector. It follows the rule of superposition, so if we can find both electric fields, we will get the total. From Q1, since Q1 is a negative charge, the electric field from Q1 is actually going to point towards Q1. So I'm going to draw that. It's going to be a left-facing arrow. And I'm going to label it E1. The electric field from Q2 is also negative, so that electric field is also going to point towards the charge, which means it's actually going to go in the opposite direction to the right. Now, direction is going to be really important here. We're going to have to be very careful about our signs and what they mean and what they don't mean. But before we've done anything else, we know that one electric field points left, one electric field points right, so they're going to cancel out, at least partially. Now, let's actually get going solving this. We know that these two electric fields, each one is caused by a point charge. So if I want to find E1, it's just the equation for the electric field from a point charge. E1 is equal to, it's going to be K Q1 over R1 squared. And we're ignoring Q2 here. We're just finding the electric field produced by E1. We know that K is 9.0 times 10 to the 9 Newton meters squared per coulomb squared. And that's going to be multiplied by negative 15 nanocoulombs, so negative 15 times 10 to the minus 9 coulombs, divided by r squared. R is our distance, and r is going to be the distance from the charge to the point that we care about. Now that's not explicitly given, but we can see the distance from Q1 to P is 0.010 meters, so I'm going to actually add that into our givens. R1 is equal to 0.010 meters. And then we can go back to plugging that into our equation over here. So that's going to be 0.010 meters all squared, and we will get a value for the electric field. In order to find that value, I'm going to have to use a calculator. 9 times 10 to the 9 times negative 15 times 10 to the minus 9 divided by 0.010 all squared gives us an electric field equal to negative 1.35 times 10 to the 6, and the units are going to be newtons per coulomb. Now let's think about what this electric field, what this means, and let's write it in a way that's going to help us a little bit more. We have a negative answer, but that negative answer just comes from the fact that we had a negative charge producing the field. And that's going to tell us that the field points towards the charge. But we already know that. What we really care about is the actual direction that this field is pointing. And in this case, since we know that it's pointing to the left. So I'm going to rewrite this electric field E1. I'm just going to write the magnitude, 1.35 times 10 to the 6 newtons per coulomb. And I'm going to write the direction in words so it's not confusing. It's pointing to the left. And let's just underline that so we know that we're going to come back to that later. We're going to have to do the same thing to find E2. It's even going to be the same equation. E2 equals KQ2 over R2 squared. We know Q2. We don't know R2, but R is the distance from the charge to the point. So R2 is actually going to be that distance, R2. Actually, I'm also going to label R1 a little bit too late, R1. And R2 we can see is the total distance minus the distance to the point. It ends up being 0.025 meters. So that's everything we need. We can start plugging in numbers. K is again 9.0 times 10 to the 9 Newton meters squared per coulomb squared times negative 20 times 10 to the minus 9 coulombs, all divided by 0.025 meters squared. I'm going to have to scroll down for this. We get an answer, a number of 9 times 10 to the 9 times negative 20 times 10 to the minus 9 divided by 0.025 squared. Gives us negative 2.88 times 10 to the 5 newtons per coulomb. And if we want to keep that to the same exponent, we could also write that as negative 0.288 times 10 to the 6 newtons per coulomb. The way it'll be easier to combine these. Again, I'm going to get rid of that negative sign. That negative sign tells us it's just towards the charge producing it. But we know that in this case, that means it's going to be pointed to the right in a completely different direction. So the negative sign actually doesn't tell us the explicit direction here, so we have to be careful there. So E2 is going to be 0.288 times 10 to the 6 newtons per coulomb, and the direction is to the right. Now we need to find the total electric field. We have one electric field from charge 1, one electric field from charge 2. The total is just going to be the vector sum. So I can sketch out a little vector diagram to find the total electric field. E total is equal to E1 plus E2 if these are all vectors. E2 is about 1.35 to the left, so we're going to have one vector that points to the left, E1, and E2 is a much smaller vector that points to the right, so if we connect them tail to tip, E2 is going to be this, and we know that our resultant vector is what you get when you connect the tail of the first to the tip of the last. So our resultant vector actually goes from here. That's going to be our E total. And we can see that it's going to be pointing to the left. Mathematically, we can treat left and right like positive or negative, but we have to be explicit about assigning a direction. I'm going to just assign right to be positive and left to be negative. Then when we add these vectors, we get E total is going to be equal to E1, which is, it's to the left, so it's going to be negative 1.35 times 10 to the 6 newtons per coulomb. And that negative sign indicates left. It's going to be plus 0.288 newtons per coulomb. Positive sign indicates that it is going to the right, so we get negative 1.35 plus 0.288 gives us a total electric field of minus 1.06 times 10 to the 6 newtons per coulomb. And a better way to write this would be to actually get rid of this negative sign again, and we need to clearly indicate the direction. So our final total electric field at point P is equal to 1.06 times 10 to the 6 newtons per coulomb. We said that negative in this case is going to be left, and it's going to be, that means that this is going to be pointing to the left. So there is our final answer. I'm going to do S for solution. And just as a gut check, let's make sure that this makes sense with what we had initially. We know that these have to partially cancel, so our final answer is going to be less than at least one of the other individual electric fields, and our final answer is less than E1. And we also know that E1 is bigger than E2 because it is a lot closer to E1. So the overall E field should be to the left. That does make sense. Don't see any problems. There's our final answer. That's how we solve this one.